day again. So welcome back to our course. So for today we'll continue for our lecture for the NumPy section of our course. So I already imported NumPy here. I already executed this code. So we're studying about the useful NumPy functions. Usually these are universal functions that you can use when you are using NumPy. So let's have, for example, the sum function. For example, we have a specific array. So again, I'll create here an array of a specific set of values. So 1, 2, 3, 4, 5, 6. Let's have 6 values. And let's try to reshape this one because I want to demonstrate the axis and column row summation. So we have a 2 by 3 matrix here. So as we can see, the array1. Okay, so let's define this one. So the array1 is composed of 2 rows and 3 columns. So when we execute this numpy.sum into array1, so it will get the sum of all the numbers. So from 1 to 6, the total is 21. But this has a special parameter which when you can do summation in terms of column and rows. So that's the second parameter in the sum functions. So for example, we have np.sum. So the same example, we have array1 and let's say we have axis 0. So 0 denotes a column and axis 1 denotes a row. So what will be the result of this one? So the result of this one is 579. So why? So we are adding in terms of column. So 4 plus 1 is 5. So 2 plus 5 is 7. So 3 plus 6 is 9. So if we copy paste this one and we change the axis, let's say for example we have 1, so it will yield a different result. So in terms of row, so this one is 6, so this one is 15. So we have also negative, positive, which are numerical element wise. So let's just say use the same array there. So we'll be reusing array so that we won't be defining any more sets of data. So for example, we have a numerical negative. So np.negative. So we use the array1. So it just translate the specific values element wise into negative values. So I will not execute the positive error anymore. So you know the difference. If you have a positive number, a negative number, and you use np.positive, it will just convert it into positive numbers. So you're familiar with this one. So the next one, so we have also the remainder or the modulus. I know you're familiar with this one. So it takes 2 parameters. So again, I will use the array1 variable previously. So let's say np.remainder. So we have array1. So if we divide the NumPy array, which is a 2 by 3 matrix denoted, so we will have a it will return if there's a remainder. So for array 1 divide 2, so it has a remainder 1. So if you look closely, all even numbers has no remainder. So you can also use the mod, which is also the equivalent of the remainder. So the same, we have the same values. So for example, we use another alternative function. So it's just the same. So the remainder and mode is just the same. That is why it is included in the heading. So it's just the same. So we have also the absolute value. So for this one, so let us define another array. So for example, we have array 2. Okay, so maybe composed of different values. Specifically, we have negative numbers. So for example, so I will not reshape this array anymore. I will directly define this as a, for example, a 3 by 3 matrix. So directly, you indicate it by 2 square brackets if you want to create a multi-dimensional array. So for example, -1, -2, so -3, then separated by comma again. So 4, 5, for example, -6. Okay, so we have array 2, so we use the absolute. So np absolute, so array 2. So Alt enter. So it just all the negative values will be converted to positive because we have this absolute value functions. So we have also, but very rarely used. So we have also the conjugate property. So we have also a conjugate which returns the complex of a conjugate. So remember in Python we use imaginary numbers. It is denoted not by I but it is denoted by J. So for example, so we have array 5. So np array, for example, we have a complex number. So 1 plus 2j, so 1 minus 3j. So that's for example. Then we'll use the conjugate. So np dot conjugate of array 5. So it's just the same for the absolute value, or the negative or the positive. So it just finds the conjugate of a complex number. So from positive, it has become negative, and from negative, it has become a positive. So next one, we have the exp, or the Euler's number. So this number is very important in engineering. So we have the denoted by exp. This is equivalent also as log e if you are familiar with logarithms. I hope you're familiar. So that's also denoted by the natural logarithm. Okay, so this one is the Euler's number denoted by e if you're familiar. Yeah, in your calculator there's an e, so that's denoted by the Euler's number. So for example, so we have to calculate a certain value. So for example, we have np dot exp. So let's say the Euler's number of for example 0.83. So I'm using this specific value for the next example. So we'll solve for the value of x. Okay, so approximately we have 12. So it means that we raise the number to, if I write this down, make it clear once again. So if I write this down, this will be equivalent to e raised to the 3 times, okay, this one is 0.83. So this one is the equivalent is 12. Okay, so I'll just erase the annotations. Okay, so for example, we have natural logarithm here. So for example, let us solve for the value of x. We have e raised to the 3x is equivalent to 12. So how will you solve that? So this is just a review of logarithm. I hope you're familiar with logarithm. So how will we compute this one? So for example, we have e raised to the 3x is equivalent to 12. So remember, e can be written down as a natural logarithm. So we multiply both sides by ln, okay, denotes natural logarithm. So we will have 3x is equivalent to 12. Okay, so this one is ln. So if we divide this by 3, okay, so the value of x, okay, so your value of x will be the ln of 12 over 3. So let's compute that using Python. So from time to time, I will introduce math concepts because again, you will appreciate more Python if the manual way of computing is done than versus automatically done by Python. So if how do you compute this one for the value of x? So the value of x will be, let's go directly on the computation. So x is equivalent to np dot the natural logarithm, okay, of 12 divided by 3. So let's execute that one. So x, okay, so the value of x will be 0.82. So remember I used previous example. So if we apply this one, okay, so previously I used this example. So why? Because I will use this again. So if you remember this one, so this one is e raised to the 3 times 0.83. So that's the value of x that we derive from this equation. Okay, so e raised to the 3 times 0.83 is 12. So this value of 12 here. So that will be the value of x. So the two are equivalent. Although it has a certain precision, but theoretically it's 12. Okay, so if you are solving the value of x in terms of e, so you multiply both sides by the natural logarithm to cancel this one out. Okay, so this will be the result. Anyway, if you don't understand this concept, so you can review your logarithms. Okay, so let me erase the annotations. Okay, so for our next example, so we have logarithm base 2. Okay, so let's have a review again of logarithm. Let's say, for example, you have this kind of logarithm. For example, logarithm base 2. How about, for example, is you will find 32. So what is the logarithm of this one? So theoretically, logarithms is just the exponentiation. Okay, so the equivalent here is how do you derive 32 in terms of exponent? So our base is 2. So 2, I think raised to the 5 is still 32. Okay, so how about fraction value? So for example, you have logarithm of 2 about 1 over 32. So it's just the reciprocal of this one. 1 and 32, so 2 raised to the negative 5 will result to 32. So remember 1 over 32. So this one is 1 over 2 over raised to the 5th. Okay, so to confirm that, let us execute some examples. For example, we have y is equivalent to np array. So let's define two values, so 32 and 1 over 32. So Alt enter. So np dot logarithm or base 2 to the y is equivalent to 5. Okay, so our value here is 5. So the next one is negative 5. Okay, so the next one, so logarithm, but this time we have a base of 10. So it's just the same. So for example, we have a logarithm of let's say 100. Okay, so how do you compute the logarithm of 100? So if there's no base, which is denoted, it is assumed that it is base 10. For example, what is the logarithm of 100? So it will be 10 raised to the 2. Okay, so the answer here is 2. So again, the same. How about we have the logarithm base 10 of 1 over, let's say, 1000. So this is 1. So the result is 10 raised to the negative 3. Okay, so let's confirm that again by using this Python. So np.log 10. Okay, so I'm not using here array. These are individual computations only. So I'll enter. So that's 2. So np.log 1 over 1000. Okay, so I'm expecting, I'm sorry, this is a natural logarithm. So log 10, I mean. So I'll enter. So that is a negative 3. Okay, so please review your logarithms. It's just how can you express it in exponential form? Okay, so of course this is very familiar, the square root. So for example, we have defined array sqrt. So the same equals np array, say 4, 16, 36, and 64. So I'll enter. So np.sqrt, remember sqrt. So which is array of sqrt. So we find the square root of the number. So I know you're familiar with that. So also the square. So let's copy this one. So copy. So it returns just the square of the number. So for example, I have 2, 4, 6, and 8. Okay, so I'm defining an array. Let's this one. So array sq. So we have np dot square. So array xq. Okay, so that it's only the square of the number. So 2 square is 4, 4 square is 16, 6 square is 36, so 8 square is 64. Also, we have some reciprocal, but I will use this one again. Okay, so we have the reciprocal of a number. So let's say np dot reciprocal of the array sq. Okay, so y0. So this one, this time, so it denotes the reciprocal of 0. Why? Because if you notice here, so the value returned is an integer 32 bit. Okay, so it has no precision value. So if you want precision, you place decimal point here. So it assumes this is 2.0, 4.0, 6.0, and 8.0. So if you execute this again, okay, we execute this again. So let's delete this one. You execute this again with a specific precision. Now that will be the reciprocal. Theoretically, this is 1/2, this is 1/4, 1/6, and 1/8. So converted to decimal places. So of course we have also functions for. So let me just erase this logarithm. Okay. So we have also this greatest common denominator. Okay, it returns the greatest common, divisor, not denominator. Okay, for example, we have GCD np.array. Again, I'm defining array. So what is the GCD for 12 and 20? Okay, so that we'll find that one. So I'll enter. So if you use this one, so for example np dot you go directly to GCD, and we use the array of GCD, this one will result in error because again it has invalid number arguments. But the reason here is we are passing a NumPy array. So if you want to compute the GCD using an array, you add the reduce method in order to find the GCD of 1220. And the greatest common divisor of this one, okay, if you find the 12 and 20, the result will be 4. Okay, so that's the GCD. So if you want individual numbers, so you can do that too. Okay, this is another alternative. So np.gcd, I mean not individual, non-array type. So for example, np.gcd 1220, so it will result also into 4. So we have also the least common multiple. Okay, so for example, again, so same thing with the GCD. So again, np.lcm. So let's use the same example. Oops, sorry about that. So np.lcm. So this one is 12. We have 20. So we have an error here. So we have no NCP because I did not define the NCP. We have NP. Okay. So NP, oops, we have LC. So we have np.lcm. Okay, so we have 60. So again, if you're using array, so for example, we have defined the LCM, np array. Okay, so how about 3, 12, and 20? So what will be the LCM of this one? So np.lcm. So remember, this is an array. So we use the reduce method for array. So LCM. So the LCM for this is just the same, which is 60. So also NumPy also has a lot of trigonometric functions. So included in the library is, how about you want to use pi? So you just type nppi without the parenthesis. So it returns the value of pi. So we have also the sine, cosine, tangent if you have trigonometric problems to solve. But I will not execute each one by one because you know this one already. So for example, np sine. So you can broadcast because this is an array. So 45 and 85. So what will be the sine of 45 and 85? So that would be 0.85. So remember, these results are in radians, so these are not in degrees. So remember that. Okay, so another one, we have, for example, let's compute single value. So for example, np sine 45. So these are in radians, remember. So we have also the trigonometric inverse. So I'll not execute anymore the cosine and the tangent. So it's just if you have the need to execute a cosine or tangent, maybe in the future, so use this one. Okay, so we have also trigonometric functions, which is the inverse. So let's go directly. So for example, I have a arc sine, or the np array, let's say 0.30 or in 0.43. So we have the value, so in terms of radians also. Okay, so you can also use single value, so arc sine. So for example, we use 0.30. Okay, so we're using singular value. And also we have in Python the hyperbolic sine and cosine. Okay, so let's say for example we have this example problem. So np arc sine h. So I'm only executing one, which is the sine. If you have the need for the cosine hyperbolic function and the tangent hyperbolic function, so you execute that one. but for this example we will use only the sign. Okay, we have 0.18 and we have 0.23. So again, alt enter. So again, these are in radians. So if you want to convert from angle from radians to degrees, so remember, if the definition is degrees, so you're converting, the end result will be degrees. Okay, so for example, we have a certain degrees. Okay, so for example, we define a specific degrees. Okay, so for example, we have, let's define this one, 2DEG. Okay, so np dot array. For example, we have a region value here. For example, let's say 40 and 60. Let's say 45. Okay, so you convert this to degrees using np dot degrees, which is plural, to deg. Okay, so that's the equivalent in terms of degrees given a radian value. Okay, so the opposite one, we have the opposite one. So we have the radian value where we have the degree value where we are interested in radian. So let us use this one. So for example, to radians, okay, we have np dot array. We have 2578 and 3437. So let's have some precision here. So 0.31. So this one is 0.74. Okay. Wait, I missed the square bracket. Okay. So I'll enter. So we have np dot radians of 2 radians. Okay, so we have exactly the same, 45 and 60 closely. Okay, the same. Also, we have a very useful NumPy statistics function. So which is this one is very common in terms of data science. This is the basic of statistics. So we have mean or average. So for example, we have a specific data of np.array. So I'm going to create a two-dimensional array without doing the reshaping method. Okay, so we have this one. So if you look at the data, you have a matrix already. Okay, it just means that np mean, for example, data, what is the mean of all the numbers. So 3.5. So again, you can specify a specific axis. So for example, np dot mean, you have the data and axis is 0. Okay, so it just means that we're averaging in terms of I think this one is column. Okay, so 4 plus 1 is 5, divided by 2 is 2.5. So if you want to find the average in terms of row, so remember that is axis 1. Okay, we have 2 and the average of this one. So this one is 6 divided by 2. So this one is, I think, is 15 divided by 3. I mean, so 2 and 5. So you can also compute the specific median. Okay, also along the specified axis, but I will not execute the specified axis anymore. So for example, we have data 2, we have np array. So again, I'll go directly with multi-dimension. So 3, 4, and 5. Okay, we have np dot median using data 2. Okay, so we have 4 as the value. So we have also variance. So variance compute computation along the specified x-axis also. So let me insert another cell below here. So for example, we have a specific value. So let's say var data, which is variance data. So np var. So I'll go directly here. So np dot array. So for example, we have 81. Let's say scores of the exam. So 87 and 90. So what is the variance of this one? Okay. So var data. Okay. So the var data is 9.76. So we have also the standard deviation. Okay. Later I will explain how you arrive this one. Okay. So insert below. Okay. There are some notes here. So the standard deviation is a measure of the spread. So how spread out the data. So low standard deviation means the data is clustered around the means that most of the data is around the area of the mean, while high standard deviation means the data is dispersed over a wide range of values. So I want you to review the 68, 95, and 99.7 rule. It is a bell curve. Okay, if you are familiar with the bell curve, so that's the great basis for standard deviation. So for example, we have the same value. So 81, 85, 83, 87, and 90. So the first one, we compute the variance. So this one, I want to compute the standard deviation, which is the STD. Okay, so I'll enter the var data now in terms of standard deviation is 3.12. Okay, so what is the formula for the standard deviation? If you remember, so the formula for the standard deviation, let me see. So maybe I write this here. Okay, so if you remember, so the formula for the standard deviation is S, for example, STD is just the equivalent of the square root of the x, okay, and the mean value, so squared over n. So this one is the variance. Okay, so in summary, so the square root of the variance will be the standard deviation. So this is the formula of the variance. So x minus the mean squared over n. So let's try solving this one. This is just a review for your statistics. Okay, so what will be the mean of this one, of our previous data? So for example, we want to compute the STD. Okay, so the mean here, okay, so let me compute the mean. So np dot mean. Okay, let's compute this manually. Maybe this is a review for you. Okay, so let's find the mean of this one. So the mean of this one is 85.2. So if we compute this manually, so we have 81, 85, 83, 87, 90. Okay, we want to compute this manually, so let me demonstrate. So we use I think green is fine. Okay, so we have equivalent of the square root, so that's a lot. Okay, so we have 81 minus 85.2. Okay, so squared, so plus, I think what's this one, also 85. So we have 85. Okay, so minus 85.2. Okay, squared, plus next one we have 83. So we have 83 minus 85.2. Okay, so squared. So let me just zoom out. Okay, so still square root, so we have plus so plus 87 minus 85.2 squared. Okay, so last one, so plus, so we have 90 least. Okay, so we have 90 minus 85.2, okay, squared, so over, so we have over the number of data we have. So I think we have 5. 1 2 3 4 5. So this one is over 5. This is the whole population. There's a different formula for standard deviation if this is a sampled only on a particular population. But if you compute this one, so I'll not compute this one manually. So this is the result. So the answer for here is which is 3.12. And if you compute the variance previously, okay, if you compute the variance, so the answer will be this one. If you compute this one without the square root, okay, so the answer will be 9.76. Okay, so that is the variance. So square root of 9.76 is 3.12. Okay, so if you remember this one, so what is the square root of 9.76? So again, so 9.76, so raised to the 1/2. Okay, so we have 3.12. So we will having detailed discussion on this on the succeeding sections because we were using statistical functions. Okay, so we also have the A-min and A-max. So it returns the minimum of an array or minimum along of an x-axis. So for example, okay, so we have, for example, data 3 is equivalent to NP array. So again, I'm using this double bracket. So I can go directly create a multi-dimensional array. So 10, 5, and 6. Okay, so for example, we have np.amin, okay, in terms of data 3. So it means that the lowest minimum value we can find is 1. Okay, so if you use Amax, copy, so paste. Also it uses also the axis, so we can define here axis 0 or axis 1. Okay, but I will not do that anymore. So Amax, so for example, is data 3. Okay, so okay, I'll do that. So for example, we have an axis, for example. So how about this one? So we have a max of data 3 in terms of axis 1. So for example, we are using in terms of row. Okay, so the answer will be 410. So why? So again, if you execute this one and look at the data 3. Okay, so we're on the row. Okay, in terms of row, the highest here is 4. In terms of row, the highest here is 10. Okay, we have also have a function of this denotes peak to peak. Okay, so this one is a peak to peak. So theoretically, this is a range. If you're familiar with the range in statistics, so data, for example, we have 5. So NP array, for example, we have 4, 6, 9, and 12. So let's execute that. So what will be the range for this one? Okay, so data 4. So peak to peak is just equivalent for a range. I have no data 4, sorry, we have data 5. So the range here is 8. Okay, so for example, much larger sets of data. So data 6, so NP array, for example. So again, multi-dimensional, 4, 6, 9, 12. example, we have 1, 2, 3, and 4. Okay, that's data 6. So NP peak to peak, which is the range of data 6. Okay, so we have 11. Okay, again, you can also do this in terms of axis. So for example, so NP data 6, let's look at the column. So axis is 0. Okay, so this one is 3, 4, 6, 8. So because we're looking at columns here. So why again? Because we're looking at columns. So for example, we have data 6. So we're looking at columns here. So 4 and 1. Okay, 4 minus 1 specifically is 3. So 6 minus 2 is 4. So 9 minus 3 is 6. So 12 minus 4 is 8. It's the highest against the lowest. So that's the equivalent for the range. So you have also percentile. Okay, which compute the specific percentile of the data along a specified axis. So let's say, for example, you have a data set of again scores of let's say grades, or not grades, specific values. So for example, 2, 4, 6, 8. Imagine these are exam scores, okay, with 50 being the highest. So 13, 16, 22, 35, 40, let's say 42 and 48. So this would be our data set. So I want to identify the percentile, for example, of the data set. I'm interested at the 70% percentile. So it just means that if you score 35 in the exam, you are 70% likely above the normal scores, or the scores that it just means, I'm sorry, that you are 70% higher than the sets of scores that for example your classmate have. So for example, we have 50th percentile. So what is the 50th percentile? The specific data. So we have 16. Okay, that's the score. So how about the 25th percentile? The 25th. Okay, so 25th. Okay, so that's the 7. If you score 7, you're only 25% higher than among the rest of the scores. Okay, so how about we have percentile 100? Okay, for example, so copy, paste. So as expected, if you do this one, okay, so this one is 48. But so theoretically there is no such thing as a 100 percentile. So why? So if you score 48, okay, although if you perfected the exam, for example, you cannot be higher than yourself. But again, if you cannot be higher than yourself, so there's technically no such thing as 100 percentile. So what they use is the 99 percentile. Okay, but these are just in theory. Okay, but if you provide 100, so it would Python would still complete. So how about you provide, for example, is there a 101 percentile, for example? Okay, so again, the only value here is I think from 0 to 100. Okay, yes, so percentile must be in range of 0 to 100. So again, how about 99, for example? So the score will be 47.40. Okay, so if you notice, we don't have the mode. Okay, so NumPy doesn't have the mode, but instead we will import this on SciPy. Okay, so import this from SciPy. So the code is from the library of SciPy, we import the stats, okay, in order to find the mode. So SciPy is a very useful library, so which is used for statistical also and machine learning. Okay, so from now on, know that there are many libraries in Python. Okay, probably this is the last one for this lecture. So data set, for example, I have a data set or specifically mode. It's equivalent to NP array. I know you're familiar with the mode. So for example, I have multiple 3s and 4s and 6, 7, 8, 9. So what will be the mode of this one? So instead of NumPy, so again we will use the stats as the equivalent of the SciPy library. So this is mode. So we have a data set of mode. So the result will be as expected. The mode of the array is 3. So the count of I think this is a unique value. So this is 1, 2, 3, 4, 5. Okay. So 5, but there are 0 to 5. So this is 6. Okay. So the count of array is 5. But theoretically there are 6 unique values here. So 1, 2, 3, 4, 5, and 6. So again, ranges from 0 to 5, which is composed of 6 items. Okay. So I hope you're learning a lot from our lectures. So the next one, we'll try to solve linear equations in Python. Linear equations in paper is a very tedious task, but you will appreciate more of a NumPy library. So we have a part 5 of NumPy, so I'm exhausting a lot of function for NumPy. So again, I'm touching only the surface. So not all of the NumPy functions and methods will be discussed because there's a lot. I'm only discussing the most common ones. So again, I thank you for listening. And if you're interested, what is this one? So this is an epic pen. If you want to present for presentation, so I'm exploring a lot of educational technology, usually in annotation. So if you want to search this one, search for Google Epic Pen. Okay, you can use this one. And if you want to save your annotations on the web, again, you can use the Annotate Beta. Okay, so this one is a paid program, so you can see here. Okay, let's hide this one. This is Epic Pen. This is a different program. Okay, so if you use this one, so my license here is expired already. So I cannot use annotations anymore here. That's why I resorted to using the Epic Pen. Okay, so you hide the annotation. So this is just a commercial and promoting the technology. Okay, this is a free version only. So they have limited features, but for teaching and for teaching and presentation, I think this is enough. So we can actually write here. So again, see you in the next lecture. We'll be discussing about solving linear equations, how easy it is using the Python library, specifically the NumPy. See you around.